So we've learned about exponential functions in the last two sections, and we're going to spend the next couple of sections learning about the function that represents the inverse of an exponential function. And the inverse of an exponential function is called a logarithmic function. So we know, for example, that 2 squared equals 4 and 2 cubed equals 8. But what if I want to know for what value of x does 2 to the x equal 6? How do we find a missing exponent? That's the question. Essentially, we're trying to undo having a base of 2. We want to bring the x down from the exponent. And the purpose of a logarithm is to find a missing exponent. So the definition of a logarithm is very, very closely tied to the definition of an exponential function. So we have here, we want to let b and y be positive real numbers where b is not equal to 1. The logarithm of y with base b is denoted by this notation, and you read this out loud as log base b of y. And it's true that the log base b of y is equal to x if and only if b to the x is equal to y. Both of those things have to be true at the same time, okay? What is important here to notice is that the base, each of these has a base. Exponential has a base and log has a base. Exponential, the base is b, and in log form, the base is also b. So that's important to remember. The base is going to be the base in both cases. And then what I always remember here is that logs equal exponents, okay? That's what a logarithm's job is to find a missing exponent. So that's why the log is now equal to whatever the exponent was there, okay? So let's look at a few examples where we can rewrite this in its opposite form. So we're going to start with equations that are in logarithmic form, and we want to rewrite them in their equivalent exponential form, okay? So if I look at number 1, it says the log base 2 of 16 is equal to 4. So remember, we're trying to put this of the form b to the x equals y. So the first thing we need to decide is what is the base. The base of the log, which here is 2, is going to be the same as the base of the exponential. Now it's going to be 2 to some power, and logs are always equal to exponents. So that means my exponent is going to be 2 to the 4th, and then it's going to be equal to the only piece I haven't used yet, which is 16. And that is a true statement. 2 to the 4th power is equal to 16, which is why the log base 2 of 16 is equal to 4. Okay, let's look at number 2. Similarly, we start with the base. The base of this log is 4, and the log is equal to an exponent, so that means the exponent should be 0, and it's equal to the only number that's left, which is 1. And 4 to the 0 does equal 1. Both of those statements mean the same thing. It's two different ways of describing the same relationship. Now, I'm going to have you try 3 and 4 in a second, but let's come down here to go the opposite direction first. So now, if I look at example 5, I have an exponential equation, and I want to rewrite this in logarithm form. So I'm going to have the log base. Again, the base is the same in either case. So this will be base 5. Notice it's like a small subscript. It's lower than the word log, and it's a smaller number. So I've used the 5. I know that logs are equal to exponents, so it has to be equal to 2, which means the 25 has to go on the inside. These two are always going to switch sides, okay? So if I look at number 6, we have the log base 10, because that's the base. It's going to be equal to -1, which means it's going to be the log base 10 of 0.1. So pause your video and try number 3, 4, 7, and 8. See if you can rewrite these on your own. I'll be back in 3 seconds with the answers. Okay, here's what we get for number 3. 12 to the first equals 12. Number 4, without the parentheses, it is incorrect, okay? If you don't put parentheses, you're only applying that power to the numerator, and we want it to apply to the whole fraction. So you do need those parentheses there. And then you can see 7 and 8 there at the bottom. So go ahead and check those. Again, you can notice on every single one, these two just switch. These two switch sides of the equal sign because it is an inverse relationship. So remember, when we talk about x's and y's in inverses, they reverse. And so it's the same thing here. Okay, so we saw two important properties in the previous examples, and you didn't even realize probably that they were important. But because of the properties of exponents, the first is the logarithm of 1. It doesn't matter what the base is. Any log base b of 1 is always going to be equal to 0 because anything to the 0 power is equal to 1. Put that on a flashcard. That is a really, really important thing. It doesn't matter what the base is. It could be log base 5 of 1, 0. Log base 100 of 1, 0. Log base 27 of 1, 0. It doesn't matter what the base is. Any log of 1 is always going to be 0. And secondly, the log base b of a base b. So if I have the log base b of b, that's always going to be equal to 1. Because again, if I rewrite that in my exponential form, I have the base b here, and then logs equal exponents, and then it's going to be equal to this b. But b to the first power is always going to equal itself. And so if the base of your log matches the number inside, it's always going to be 1. We always have to think in terms of exponents, okay? So when I ask, what is the log base b of a, the question is, if b is the base, what exponent gives me the answer of a? And so your perfects chart is really helpful. Again, here, I think the one I gave you this year is green. But if you refer to your perfect chart, it'll help you with the powers. So we can evaluate each of these logs without a calculator. And so let me tell you how I know this. The log base 4 of 64 says, if I use a base of 4, what exponent makes my answer 64? And so if you look at the row of 4s in your perfect chart, you see that 4 to the third power is equal to 64. So the log base 4 of 64 is equal to 3. Now it gets a little bit trickier when we look at different types of numbers. We have to remember what negative exponents do. We have to remember what fraction exponents do. So we have all kinds of different things that we have to be aware of. So on number 10, the log base 5 of 1/5 equals what? Well, if 5 is my base, what exponent makes my answer 1/5? What would move that 5 down to the denominator? That would be a -1 power. The log base 5 of 1/5 is equal to -1. How about this one? The log base 1/5, 125, and so we want to know if 1/5 is the base, what exponent will make it positive 125? Well, the first thing is that if I started with a fraction, 1/5, and I have to end with a whole number, I need it to flip over. So at the very least, I know that my exponent has to be negative. And since 5 to the third is 125, I know that exponent is going to be -3. Lastly, this one is the log base 36 of 6. So 36 to what power equals 6? The first thing I noticed is that my base was 36 and I ended up with a number that was much smaller. So that's a clue to me. It's not flipped over, so I don't think a negative exponent is going to work. But that's a clue to me that maybe I need to think in terms of radicals. And since the square root of 36 is 6, I know that I can use the 1/2 power. 36 to the 1/2 power is going to equal 6, okay? So remember, your fraction exponents are really, really important. In your calculator has keys for only 2 bases, okay? So there's two special logarithms, and these you want to put on a flashcard. You want to recognize these when you see them. The two special logarithms that we have are called the common log, and that's when you have a base of 10, and the natural log, which is when your log has a base of e, and we've talked about this number e before, okay? You will not see base 10 or base e written down. You will see log of x and natural log of x. And you are expected to know that when there's not a base written on the log, it's implied that it's 10. Just the same as when there's not a number in front of the x, it's implied that it's 1. When there's not an index on a radical, it's implied that it's a square root. Same thing. Log of x means log base 10 of x. And then ln stands for natural log of x, and that implies that the base is e. So you should be able to find those buttons on your calculator and be able to plug in log of 8 and natural log of 3. So pause the video and take a moment to type those in your calculator and see what you get. 3 seconds. All right, these are what I get. It's said to round to 3 decimal places. We've already looked at where the e to the x button is. Your log and natural log buttons should be roughly in the same spot on your calculator if you can't find them. So those are the two that you can do on your calculator. And in the next section, we'll talk about what to do if it's a different base and we need our calculator. So the last thing for today, this kind of introduction to how logarithms work, is that since exponential and log functions with the same bases are inverses of each other, they undo each other. That's the whole point. That's why we need it. So if I have b to the x, I can take the log base b of b to the x, and the log with base b undoes the exponential base b, and my answer is x. So these essentially cancel out, and we just get left with x. And the reverse of that is also true. If I have a log base b of x, and I use that as an exponent on a base of b, that's called exponentiating. But if I have a base b to the log base b power, again, those undo each other, and the answer is just x, okay? So let's look at a couple of ways that that can happen. So on number 15, we have 10 to the log of 4. Now remember, this is a perfect example. This is a common log, so it has a base of 10 even though it's not written there. So the 10 and the log base 10 undo each other, and the answer is just 4. That's all we have left, okay? Now number 6 is a little bit trickier because I have a log base 5 and an exponential with a base of 25. So that doesn't match, but is there a way that I can write 25 using a base of 5? And the answer is yes. I can rewrite this as the log base 5 of 5 squared to the x power. And then remember our properties of exponents. When I do a power of a power, I really am multiplying my exponents, so I get 5 to the 2x. Now the log base 5 of 5 to the 2x, they undo each other and just leave me with the exponent, 2x. Logs and exponentials with the same base cancel each other out. Number 17, the natural log of e to the 2x. Remember that the natural log is another way to write the log base e. We never write it that way. We always write it ln. But because of that, the log and the exponential have the same base, and I have 2x. So take a moment and see if you can write down what you think the answer will be to number 18. 4 to the log base 4 of 5. We should just get 5. The base 4 and the log base 4 undo each other. Okay, so those are the things that you're going to be practicing tonight. I would suggest that before you start working on your homework, go back and look through the stuff we just copied down, make a few flashcards, do some highlighting, make some notes to yourself in the margin, but take a moment to go back and kind of process what we just talked about, and then you can start working on your practice. I'll see you soon.